Oh, the little morning greetings?
Yes.
Tried to spice it up a little bit. Did I do? Oh, I didn't do the dad jokes with y'all, did I?
You didn't do, oh my goodness. You told me we could have done that.
I did dad jokes in my other class because they were struggling. So I found a dad joke of the day. I don't know if anybody really cared or noticed, except Sid. Sid would go, keep them coming, man. He's hilarious. Anyway, okay, so if you turn in your book to page 65, we're going to be starting our talk about derivatives. This first day, I'm going to talk to you about actually what a derivative is, and should you not pass the AP exam, which most of my students do, if you don't pass it, and then you go to college and you have to take Cal 1, you will spend a ton of time miserably doing derivatives this way I'm going to show you. Because what I'm going to show you is the actual definition and how the real derivative comes from this. And then starting tomorrow, I'm going to start introducing you to rules, derivative rules, that keep you from ever having to do this again. Okay? So we're going to talk about this today. There might be one or two problems you have to do tonight just to show that you can. And you'll probably even recognize one part of this derivative from things that we have done in the past. But especially you guys that didn't have me last year, you guys never learned limits or derivatives. And in a normal year, you probably wouldn't learn much about derivatives. And I don't even know if they even talk about this definition, but I need you to know the definition because AP loves to see if you know this definition. And they'll throw problems out there that will be in this form. However, because they look like a limit, we are going to have a way to combat that. Because anything that looks like a limit that's actually a derivative, we're going to learn something called L'Hopital's rule, and it will help you be able to do this. But I kind of want to show you what this is, because every now and then, like I had a guy named, if you remember Alyssa Balon last year, her brother Carlo was a year or two older than her, 2 years older, and he made a 5 on my AP test, but he was like, man, I'm taking Cal 1 again in college for an easy A. And he got an A, but I ran into him in a football game, and he was like, man, it's like all we use is the definition of a derivative to do every stinking derivative, and it's so long and tedious. So I'm going to show it to you today. We're going to talk about what a derivative is. It is one of the just the actual mechanics of it. You should have a shot of doing really, really well on this test, making an A on this test. Usually my class average is an A, and then if you struggle a little on limits, it'll be a nice little offsetting grade, and get that average back up. But anyway, without further ado, let's take a look. Okay, so if you look at this page, what was it, 65?
Yep.
Okay, so if you look at the book, I'm just going to show you the book first, and yes, I want to show you the book on page 65, and then I'm going to show you in real life what I've tried to print for you, because you're not going to be able to take this little program I have home for you. So I'm going to show you both, but on page 65, if you want to turn to that, it talks about what a derivative is. All right, so basically a derivative is just another way of saying what is the slope at any particular point on a graph. Now you're used to defining slope as the slope of a line. Well, there is a slope of a line, and the slope of a line is unique because it doesn't change, right? But a slope basically means if you have any two particular points, what is the rate at which it's changing? The change in y over change in x, and you called that rise over run or whatever. But it really was how much you went up versus how much you moved over. But when you're not talking about x's and y's, and you're talking about miles and hours, or feet and second, or number of gallons per minute, or whatever, those are rates of change. Velocity is a very common rate of change that we deal with in physics and in real life. Or we deal with speed, which is kind of like velocity. But anyway, most functions don't move along a nice straight line. Okay, they move along a curve. So when we talk about a derivative, what we really mean is, if I were to have, say, a curve like this, and I want to know what is the rate at which it's changing, if this represents something at a certain point, I'm basically thinking about the line that's tangent to that point. Okay? And you can see as I'm drawing tangent lines, and y'all know what, that's not a very good tangent. As I'm drawing tangent lines here, I get different lines, don't I? At different points. And the slopes of those lines are constantly changing. Sometimes they're negative, sometimes they're zero, sometimes they're positive, zero, negative. So what we want to do is, that's what a derivative is. It's not a slope everywhere, because most of the time the slope's changing. It's an instantaneous slope, okay? So we're talking about the slope at a certain point. And sometimes in the basic derivatives we deal with, it'll basically be an x value, okay? But it's still, even at an x value, there is a point associated with it. So how do we actually calculate that? And again, the rules that we'll start learning tomorrow are much easier than this mentality. But what I'm doing here, and you're going to see a bunch of pictures, I'm trying to put in picture form what I'm going to show you on this program, okay? How to actually take 2 points that are separated and using a little creative math and a limit, calculate an actual slope at this point. So what I'm going to talk about with this program is essentially this, okay? And you might even recognize that in there. You've been seeing that probably since Algebra 2. I know I've been throwing it at you just with functions so that you get some practice on how to use it. But anyway, this page right here is what I'm going to be talking about in this program. So this is a clever little program some math teacher 20 years ago made up, and it's the best program ever. It allows you to really explain some cool stuff. And I think she's pretty much cashed in on this thing. But anyway, let's just say I had a random graph. This is a parabola, most likely, okay? Or at least what I can see of it looks like a parabola. Actually, this is an x to the 4th graph, but whatever, it appears like a parabola. I want to find the slope of this curve right here. Now, if I were to have any one of you walk up here and say, all right, if I want to find the slope of this curve at that point, you would need to draw a tangent line in there, okay? Because otherwise, how are you going to figure out rise and run? So I guess is if I had any one of you come up here, if that was legal and we didn't have to throw the marker away, okay? Somebody might come up here and go, all right, there's my tangent line. And then they would, from this, they would take a ruler out or whatever and measure the rise, you know, and then measure the run, and they would have their slope. But my guess is I could probably have any other person walk up here and go, all right, here's my tangent line. And it still looks like a tangent line. But very clearly, I've got a different rise and a different run, don't I? Because it's a different tilted line. And I could have even somebody else come up here like this and draw a line that appeared tangent. So just eyeballing the tangent line is pretty rough. So Isaac Newton, zillions of years ago, came up with a very clever way to look at this and come up with an exact slope. And it's so simple, but the actual application that we use it for is so extensive, whether it's in rates of change of a growth of an investment, or rate of change of a acceleration of a missile, or all kinds of different applications, whether it's economics or mathematics or physics. It's very extensive, and it all boils down to this little basic principle. So here is what Isaac Newton said. He said, well, in so many words, since it's so hard to find the slope there, what if I just picked another random point, call it Q, and I'm going to create this point Q a little bit of distance to the right. So he said, I'm going to add a little distance to that x, and that distance was called h. So there's an extra little distance, and I'm going to make another point up here that I'm going to call Q. All right, so he picked another point and created it, and now he has 2 points. All right, and then he said, what I'm going to do here is I'm going to now make my slope between points P and points Q. Now, when he creates this secant line, not a tangent line, the slope of that secant line, and it's calculated right there for you if you're curious, is not the slope of the tangent line at P, is it? But this is what he did. He said, well, to calculate that slope, I would have to take the point here and the point here and find the slope between them. And if you think about it, isn't the point here, point P, x, f of x? Isn't that the first point, like x, y? And isn't the point Q over not x, but what? X plus h? And if I go over x plus h, how much do I go up? F of x plus h. And if I were to now find the slope between these two things, wouldn't I get y minus the y over the x minus the x, right? And don't those x's on the bottom cancel? And that's where that little expression comes from that our teacher, well, for a lot of you, just me, but for some of you other teachers have been just throwing out there when you've been dealing with functions. But that's not the derivative. That's the slope of this secant line, okay? But I don't want the slope of the secant line. So this is where Isaac Newton and also a guy named Leibniz, they were both doing it in separate countries at the same time, and 10, 15 years later before the, obviously before the internet, somebody found their two works and went, man, these guys published basically the same stuff in a slightly different language. Sometimes Isaac Newton's formality was better, sometimes Leibniz's was a lot better. But these two guys basically published the same thinking at the same time. But I think a lot of people do give Isaac Newton credit, but we use a Leibniz notation on almost everything when you really start getting into calculus. But it's neither here nor there. This is what they did to actually find the derivative here. They said, okay, well, if that is the slope of the secant line, what happens to this slope as my distance there, the h, gets smaller and smaller and smaller? As I close that distance or make the h shrink, what happens to the x plus h? If I make h, like right now h looks like it's about 2. If I make h go to 1.5, 1, 1/2, 0, what does it eventually do? So that point, that x value becomes this, and this point q will become point p, right? And this slope turns into what? Now what does h going to 0 sound a whole lot like? A limit. So they said, okay, if I were to take the limit of this, as the h value goes to 0, then this slope of the secant line becomes what? The slope of the tangent line. And the slope of the tangent line is your derivative. And it's that simple. Now watch, there's a nice little picture right here. If I let h go to 0, you can see, and I'm going to put the tangent line up there. Okay, here's the tangent line. And you can see it. As the h is shrinking, the secant line is becoming the tangent line. Right? And bam! So once it becomes the tangent line, that is our definition of a derivative. Okay? And this particular derivative was about 1/2, but whatever, that's not really relevant here. So that is what I'm trying to illustrate on that sheet of paper you have, since you can't take this program with you. So when you look back at this, I hope when you're studying it, you can see originally I have the slope of the secant line. The slope of the secant line is that f of x plus h minus f of x over h expression that you guys have been dealing with for a couple of years, hopefully. Okay? But as soon as I make the h go to 0 and tack a limit on it, that slope of a secant line, which is that, progressively becomes closer and closer. It becomes the slope of the tangent line, if you hit 0. Now the problem is, if you look at any one of these, look at this equation. If I plug a 0 in for h, what do I end up with? Like right here, what happens when I plug a 0 in for h? Right there. And look at it. What do you get? You get 0 over 0. But what does that mean?
A hole.
And do you have limits at holes?
Yes.
Almost all the time, unless it's a weird piecewise function, right? In which case you might or you might not. You'd have to really check from both sides. So right here, because I'm going to get 0 over 0, I am going to be able to find that limit. And if I can find that limit, I can find the derivative, because that's what this is. Slope of a tangent line is the actual derivative. All right? So that's what this is in definition. And you can use this to find derivatives of anything. It's just really tedious. So what you're going to see today is how I would actually use this. And we're going to use some basic things. We're not going to get into all the ugly proofs like you might in Cal 1, where you're like, why is the natural log definition 1 over x? And you're like, well, throw it in this definition and let's see what happens. And sometimes the math is really, really awful. We're not going to do that. I'm going to show you a couple. Like today, I'm going to show you a couple here. When we get to triggers, I'm going to show you a couple. But you will never have to do this on my test, because I'm going to show you a workaround that'll let you use these little tricks we're going to start learning tomorrow. And the tricks are super, well, they're 50 times easier than this stuff. I mean, 50. They're much easier. Okay? So anyway, this is what we call a derivative. Derivatives talk about slopes of a function. Slopes are talking about rates at which something changes. So depending on what the function's talking about, if it's just a random polynomial, then you're like, I don't know, it's talking about units of x and units of y, whatever. But if it's talking about velocity, or the rate at which gallons are pumped from a ship, or whatever, the rate at which your intelligence is increasing due to studying, all those kinds of things, we can look at it with derivatives in calculus and really examine that stuff. All right? So anyway, here's how, and actually before I actually do it, I want to talk about some ways I'm going to write this. So let's just say you were given a function like f of x, right? I wrote f of x equals blah, 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 and I said take the derivative. Well, I don't want you to just write the derivative down. You need to have good form. Remember, you're going to have somebody reading your AP test. And when they take a look at what you're doing, you need to have everything labeled well. Because they don't know who you are. They're not going to go, oh, Sam, such a good guy. I know he does his work. I mean, you're just, SM on your paper and from whoever. They don't have any idea. You have to spoon feed them what you're doing. So if a function is written as f of x, blah, 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 and you take the derivative, make sure you label it. And one of the ways we label it is if I wrote it out as f of x, then write f, we call it f prime of x. Okay, it's basically like a little apostrophe. Okay, if it's something written as y equals, then a lot of times you just write y prime. And that little prime, just say this as f prime of x instead of f of x, or y prime. But this is called Leibniz notation. It's much better when we start getting into more difficult calculus problems than we're doing just starting out. It's called dy dx. And basically what you're doing is you're saying, I'm taking the derivative of my y function with respect to x. But instead of writing it, the derivative of y with respect to the x variable, and by the way, if I had a different variable, I might have the derivative of y with respect to the t variable. Because a lot of times we'll do a time. Or if it's a velocity function, derivative of v with respect to t. Okay, but a lot of people just shorten that and just say dy dx. So if you had a function like, whatever, y equals 3x squared minus 5x, and you learn your rules, you would say, all right, the derivative of this y function with respect to x would be 6x minus 5. And you will learn some of the power rules and other things tomorrow on how to actually do that. Okay? So anyway, again, just some notations I wanted to point out. And if I had a function instead of just a y, instead of writing d f of x over dx, a lot of times we just say d dx of the function. Okay? Like right here, I could have said d dx of y. But most people write it like that. If it's a function, they write it like this. And then I could also use wording like, hey, find the instantaneous rate of change. Don't be bothered by that. Right? What is the derivative again? It's the slope where? At a point. That's at a particular instant. Okay? It might be an instant in time. It might be an instant in feet. Who knows? But it's an instantaneous rate at which things changing, an instantaneous slope. So all these are another way of saying take the derivative. And I will use all of these on your worksheets to try to get you where you're not even thinking about it when you see this stuff. All right? So here's the hard way to take this derivative. And then tomorrow you're going to be able to look at this and go, the derivative is 6x minus 2. It will take you that much time. But this is how, but that will be a trick you're going to learn. This is how you're going to do this using our definition of a derivative. Okay? So the question is, find the, use the definition of a derivative, which again, here's the definition of derivative. The limit of f of x plus h minus f of x over h as h goes to 0. We're going to use that definition of the derivative to find the derivative of this, or find the slope of this line at any x value. So we're going to find a generic one. And then once I find that generic derivative, I could always say, okay, now that you have your generic derivative, what's the slope at x equals 2? You just plug 2 in. So you're basically finding a new function that gives you the slopes. Because the slope, unlike a line, is going to be changing a lot on a parabola, isn't it? All right, so here we go. If I want to use this definition right here, which is the slope of the tangent line, that's the derivative, I need to know f of x plus h. Well, if that's f of x, how do I find f of x plus h? Do I take this and tag an h on the end? No, don't make this mistake. F of x plus h is not f of x with an h on the end. That's not it, and I see people do that all the time. And every time they do it, they get 1. It's amazing. These are so easy. No, if you're getting 1 every time, you're probably doing it wrong. You need to take that and plug it in. So I'm going to plug x plus h into the function for x, and that's going right there in this problem. So here's the f of x plus h. I've plugged x plus h into my function, there and there, and I'm going to take this whole f of x plus h, and I'm going to replace it. Replace that right there. Are y'all tracking with me?
Okay. Yep.
All right? Then what does it say to do? Minus the function, right? And you've already got the function, you don't have to do anything to that. There's the function. So I'm going to take that and replace this part. And I wrote it out again, but I'm going to take that, which is this, and I'm going to put it in that place. You can see it right there. And then I'm going to drop the negative and drop the h and simplify. And if I get it all simplified at this point, I will have my definition of a derivative, which is, we already know it's 6x minus 2 because I know the trick. Now there's a lot of math that goes into this. What do you think the biggest mistake is, other than making that mistake?
Multiplication errors.
Dividing into.
The negative, actually, forgetting to distribute that negative. People don't put parentheses there. Shockingly high rate of time. Okay? It's just careless and you don't see it much. Very easy to do. Don't forget to distribute the negative. And by the way, if you do this correctly, everything here is going to cancel. So if you forget to distribute the negative, and you end up with positive 1, positive 1, you're like, well, that didn't cancel. You probably made a mistake somewhere. Okay? Because look, if I distribute the negative there, now I also have to FOIL this out. Remember, square the first. That times 2. Square the last. Then you have to distribute the 3 in. And you got to distribute the negative 2 in. Again, don't forget to distribute the negative. But look what happens after all this math is finished. When you start to go canceling, right here, everything here is going to cancel. If it doesn't, you did something wrong. And then another thing, everything left is going to have a what in it? Why do you think that happens?
So you can cancel it.
You can't plug anything.
And why do you think you know it's going to cancel out, George?
Because if it couldn't and you have a 0 on the bottom, it wouldn't be defined.
True. But what did we say at the very beginning about this? When you plug a 0 in, what do you always get? 0 over 0.
Right.
There's a hole. And on holes, you usually can manipulate them to be able to cancel out that hole. But initially, I couldn't see the hole. But once I clean it all up and cancel junk, you're like, there it is. If I factor an h out of here, that's the common value that you cancel, because that's the first thing we learned about holes, right? When you get 0 over 0, factor it and cancel out the common factor. Well, there it is. Now that I can see it, I can cancel an h. It's the same thing as factoring it out and canceling at the bottom. Just cancel one of each. And you're left with 6x plus 3h minus 2. And now you can take the limit. So don't forget the limit part. It's just coming along the whole time. And when I plug the 0 in there, what do I get?
6x minus 2.
Which is what we said the limit was from the very beginning, because I happen to know the tricks and many of you do as well. Right? And you will never have to do this on the AP test if you know what you're talking about. And every now and then AP will give you this. They'll start you with this expression right there at the top. And my hope is that you look at it and you go, wait a minute, no, not that one. They'll start you with this. This one. And my hope is you'll go, wait a minute. This function looks just like that function, except this thing looks like it had a what plugged in? An x plus h. So I bet the function that's going on here is that. And if you can look at this and go, all right, that's the function. And what does this whole expression mean? And you go, oh, it means the derivative of that. So you literally take one step backwards, find the function, and go, oh, well, I can find the derivative a much easier way. And you pull out your power rule, and you're done. So even when, and we'll practice a couple of these, but even when you do see something like, or you lose the L'Hopital's rule, because if you plug a 0 in here for h, you get 0 over 0, and then you could always go, oh, L'Hopital's rule. Now, again, if you don't know L'Hopital's rule, you will in a few days. And we'll spend the day even talking about L'Hopital's, and I'll go back through all these ugly problems. So you should never have to do this on an AP test. All right, I'm just throwing some out here because every now and then somebody kind of bails on me and quits working in January and they make a 2 on their test and they're like, oh crap, I gotta take Cal 1 again. And when you take Cal 1 again, you might have a professor that literally, Carlo did, the entire quarter, every time they did a derivative, had to use definition of derivative. They could not use those little tricks. Or at least the point I saw him in October. Maybe he softened up a little bit later, or she, I don't know. All right? Now, a couple other things, we're not going to get into it a whole lot, but you can actually take the derivative twice. That means something. Like, for instance, if you take a derivative once, it's the slope. It refers to a new equation that you can find slope with. If you take the derivative twice, you have an equation called the second derivative in which you can find concavity. So like you can tell by taking it, plugging numbers in, if it's concave upward, like this, or if it's concave downward, like this. So you could have a slope that's positive, like that's positive slope the whole time, right? Because the slopes are going up to the right. But you can see right here, it looks like it's concave down, here concave up. And the second derivative will give you indication of what's going on. Doesn't matter right now, but just know that if you ever see these expressions, instead of y prime, or instead of dy dx, if you see d2y over dx squared, or instead of seeing f prime, you see f double prime, or instead of y prime, you see y double prime. That just means the second derivative. And you can have as many derivatives as you want, although in this class we won't get into what the third derivative or the fourth derivative or anything means. But the second derivative is as much as we do. And it would depend on what you started with. Like if you start with position, you take a derivative, now you're at velocity. You take another derivative, now you have an acceleration equation. If you take another one, I don't know, ask your physics teacher. What comes if you take a derivative of acceleration? Somebody said something like movement in time or some weird thing, I don't know. I mean, technically you can think through it and come up with something. Are you with me? All right, so let's just look at a couple practice problems. You should know the derivative of number 1 right now. What's the derivative of number 1?
7.
Yeah, even if you don't know the derivative tricks, the derivative slope, right? What's the slope of a line? The m value, right? So we know that the slope of this is -7, but watch how the derivative plays out. Using the definition of a derivative, I'm going to say, all right, the limit of the f of x plus h. So here is the f of x plus h minus the f of x, all of it over h as what? As the h goes to 0. And if I plug a 0 in there right now, I get -7x plus 3 plus 7x minus 3, which is 0 over 0. So what do? I clean it all up. Don't forget to distribute. And what should cancel? All of that junk, which it does. And then what should be left over? An expression that only has h's left. And look, that's all I have left, right? And now the h's cancel. And then all you have left is a limit of -7, which is -7, which we should have known from the beginning. Right?
Right.
And if you look at number 3, I might leave you number 2 and number 4. And I'm probably going to come back to this other thing down there at the bottom. So don't worry too much about this. But number 3, it's going to be a bigger power. I'm going to do that for you. I wouldn't do that on the test to you. But if that's f of x, using our limit definition, what is f of x plus h? 2x plus h cubed, that's ugly, 3x plus h plus 5, and then minus the function, all of it over h as the h goes to 0. Now, who knows how to cube a binomial? I do, because I learned Pascal's triangle and how to expand binomials back in Algebra 2. And I know that on 3, so I don't have to write it out. Sorry. I don't have to do this like some of you would be forced to. And that's not fun. But what I know is Pascal's triangle on the row goes 1, 3, 3, 1. So I am going to do this instead. I am going to copy the 2 down, and that binomial cubed ends up giving me 1, 3, 3, 1 coefficients, and then it goes x cubed, x squared, x, no x, and then h cubed, h squared, h, and no h, and then all positives. And I am sure glad I learned that, but you won't have to do that on a test, don't worry about it.
Yeah.
And then distribute the -3, bring down the 5, distribute that negative, all of that over in h. And I'm going to take a little time so I don't have to rewrite this whole problem. If I distribute the 2 in there, 2x cubed plus 6x squared h plus 6xh squared plus 2h squared. So this is what I got left, right? And what's supposed to cancel every time?
Everything but the h.
-5, +5, positive 3x, -3x, -2x squared, positive 2x. Sorry, -2x cubed, positive 2x cubed. What should be left over? Only terms that have a what?
H.
Those 3 have h's and that one. And if it only has an h, what are you allowed to do now?
Cancel some stuff.
Cancel that h with one of those. That's the whole. So we're canceling out the, is that right? 6x squared h. Sorry, I got it in the wrong spot. Canceling, no, 6x squared h. 6xh squared. Not it right. Okay. So 1h there, 1h there, 1h there, 1h there. And now I'm left with the limit as h goes to 0 of 6x squared plus 6xh plus 2h. And what should happen when I plug a 0 in there?
H is canceled out.
And, oh, -3. So when I plug a 0 in there, that goes away, and I'm left with 6x squared minus 3. And for those of you that had me last year, you probably can look up here and go, oh yeah, that would have been 6x squared minus 3.
Wait, why is it 2h squared, not 2h cubed?
You are absolutely right, sorry. It's not going to affect that because it went to 0, but you're absolutely right. Are y'all with me on that? So again, tonight you get to do 2 and 4 just to experience the sadness and pain that's associated with this tediousness. And I'm intentionally doing it so that tomorrow you walk in here and I'm like, hey guys, who wants to learn the power rule? And you'll be like, me, I do. And you're going to see how easy derivative actually become. And then if and when we have to actually learn how to get out of these, I'll talk more about that. So don't worry about this stuff down low. All right? All right. Good day.